So I'm going to show you exactly how they figured out the ideal gas law. You guys are only going to have to know the original, not the original, but the final version of it. But I want to show you how we got there. So if we were to use conditions of STP and 1 mole of gas, we could calculate some constant R as being PV over T from the combined gas law. So what is standard pressure? No, pressure.
You said what is standard pressure?
Standard pressure. 1 atmosphere, right? 1 volume of gas at STP is going to be how many liters? 22.4. And what is standard temperature? 273 Kelvin. So here, I just plugged in for 1 atmosphere, 22.4 liters, and 273 Kelvin. So I get a value of R, this constant, of 0.0821. Now, do I have to use atmospheres for my standard pressure?
No.
No. The second most common units of pressure are kilopascals. So here I did the same thing, but using the 101.3 kilopascals as my standard pressure. That gives me 8.314. This value of R is what's known as the universal gas constant. Sometimes that's a blank. Sometimes you'll hear it as the ideal gas constant, but normally it's the universal gas constant.
Are you able to use Tor?
You could, but you usually don't. These are the 2 most common versions. So, looking at this, the value and the units of R, is it going to depend on the units of volume? No, because they're the same. Temperature?
No.
No, they're the same. Pressure? Yes. So, your units and value of R depend on your units of pressure. So, you could use atmospheres if you're having, you can use the value of R with atmospheres if your pressure's in atmospheres. You could use the value of R for kilopascals if your pressure's in kilopascals. Now, what if you had something else? What if you had millimeters of mercury? Just convert it to atmospheres. So you don't actually have to know this one at all. If you just take your kilopascals and always convert it to atmospheres, you only have to memorize one of these constants. So whatever your units of pressure are, just always convert them to atmospheres and you can use this constant. I'll show you what I mean. So the value of R is calculated assuming 1 mole of gas. So what should we do for something other than 1 mole?
No idea.
What did we do here? What did we have to do to the molar volume when we had something other than 1 mole? We had to multiply. So I would have to multiply the molar volume by the number of moles, which would multiply our value of R by the number of moles N. So our PV over T gives us N times our value of R.
What's the N stand for?
Number of moles.
So we would do that same exact does it matter if we do it in atmospheres or core or?
As long as you're using the consistent R. Okay. What we do is the final version of this rearranges, so we multiply both sides by T to get it to the other side. We get PV equals nRT. This is the most famous chemistry equation in thermodynamics. Oh, don't worry about the word. PV equals nRT. Chemists around the world call this Pivner. Yeah, Pivner. PV equals nRT, the ideal gas law. So, what happens is, P is for pressure. Now pressure, right, knowing our 2 values of R, can either be in atmospheres or kilopascals, depending on whatever's most convenient to us. The volume, V, has to be in liters. N is the number of moles, so it's in moles. Now we have 2 values of R, 0.0821 for liter atmospheres over mole Kelvin, or 8.314 liters times kilopascals over mole Kelvin. So notice, here it's in atmospheres, here it's in kilopascals.
Did we just memorize one of the
You can just convert the units of pressure. So temperature, T, has to be in Kelvin. Alright, number one point of confusion here. This is not an equation down here. These are units. They are units. You are not plugging in 0.0821 times whatever your liters and atmospheres and moles. That is not what you are doing. Right? Those are just the units like grams that go in for R. This is your equation. Okay, so here's an example. So if I have 4 moles of gas at a pressure of 5.6 atmospheres and a volume of 12 liters, what is the temperature? So I have units of pressure, 5.6 atmospheres. I have units of volume, 12 liters. I have moles, 4 moles. Right. Now, how do I know I'm using 0.0821 as my units or as my value for R? My pressure is in atmospheres, so I need the one that's in atmospheres.
Okay, that's what I was asking.
And I'm looking for my temperature T.
When you write your equation, do you want us to have that L times atmosphere?
So here's the deal. For right now, as you are learning this, I want you to write all of your units. By the time we get to the quest and you're used to it, you can start dropping units. But for right now, I want you to write them out to make sure you're all in the same units.
Why did you write that entire formula next to that?
It's not a formula. It's units.
Oh.
This is just like grams.
So how would we mark all that out? Like,
I will show you. Give me a second.
Okay.
So 5.6 atmospheres times 12 liters. Right, so 5.6 times 12 divided by whatever 4 times 0.0821 is. That isolates T. So let's take a second to look at the units. So in this case, my units of pressure are in what? Atmospheres. My units of volume are in liters. All right, my units of moles is, well, moles. R is using liter atmospheres over mole Kelvin. And I'm looking for T.
So it's going to be...
So when I multiply N times R, what happens to the moles?
They cancel.
They cancel. So now I'm left with, this turns out to be liters times atmospheres. I just flipped them around. Equals liter times atmosphere over Kelvin times temperature. So what do I have to do to get temperature on its own? Divide by
No liter atmosphere Kelvin.
this guy. Now, how many of you guys remember, right, when dividing by fractions, please don't cry, flip the second and multiply?
No, I've never heard that one.
You ever heard that?
Yeah.
Yeah. Okay, so what happens is when you're dividing by fractions, please don't cry. You flip the second. So now it's Kelvin on top, liter atmospheres, and then multiply. So when you do this, what happens? These cancel out, and I'm left with Kelvin. So my units for temperature are in Kelvin. We see how that works?
Wait, so we couldn't just leave it divided by liters atmosphere over Kelvin and then just
Yeah.
mark it out?
How'd you get 205?
Okay, so how I got 205, when I plug this into my calculator, okay, 5.6 times 12 gives me 67.2 equal to 4 times 0.0821, which gives me 0.3284 times the temperature. So I have to divide both sides by 0.3284. So my temperature, 67.2 divided by, 67.2 divided by 0.3284 leaves me with 204.6, which I rounded to 205 Kelvin.
Ooh.
Yeah. Okay. So I've got another example here using PV equals nRT. Pivner. Right. So if I have an unknown quantity of gas at a pressure of 121.6 kilopascals, a volume of 31 liters, and a temperature of 87 degrees Celsius. Oh no, that's useless to me. So what should I do to it?
Change it.
Put it in
Not.
Kelvin, which I do how?
Adding 273.
Add 273. That gives me what in Kelvin? 360 Kelvin. Great. So how many moles of gas do I have? Well, my pressure is 121.6 kilopascals. My volume is 31 liters. I'm looking for moles. How did I know to use 8.314?
Because it's in kilopascals.
It's in kilopascals. What if I didn't know this one? What could I do to my value of pressure? I could convert it to atmospheres and use the 0.0821. Does it make a difference? You get the same answer.
Do you recommend just knowing the formulas?
It's up to you. I do it both ways. And then times the temperature, 360 Kelvin. So 121.6 times 31 divided by, right, the product of 8.3, let me try that one again. 8.314 times 360.
Oh.
So 121.6 times 31 divided by 8.314 divided by 360.
What does he do?
So you end up getting 1.3 moles.